Hello everybody and welcome. In this video I'm going to be kind of looking at an inquiry lab for the PhET simulation, The Moving Man. And so with an inquiry lab there are no specific procedures or steps to follow. You want to explore what the simulation has to offer, kind of sink your teeth into as much physics as you can there. And so we're just going to kind of explore this together a little bit here. You can see that it's called the moving man, and there's a man here, and he is set upon an x-axis that goes from negative 10 meters to positive 10 meters. There's a few objects sort of along the path there. So we have like brick walls on either end of those, sort of bookends between those negative 10 to positive 10 meters. There's a tree at about negative 8 meters and a house at positive 8 meters. And so this is a good simulation just to kind of look at the very beginning sort of introduction to motion if you're studying physics and looking at position or changes in position, which is displacement, velocity, the rate of change of that displacement, and then the rate of change of velocity is of course acceleration. We can see here that we can toggle on vectors, so we'd actually be able to see sort of what the vectors look like. Let's just take a look at a man who starts at 0 meters and then moves to the house there at positive 8 meters. And so you can just grab the person and kind of pull them over there. And you can see that his position has changed to 8.05 meters, and because I'm no longer pulling him there, the velocity and the acceleration have both dropped down to 0. But you may have noticed that as I was moving the person, you could see that there was a velocity or an acceleration. And the clock sort of continues to tick here. So let me pause that. So I just sort of recorded that motion. It was a person who started at 0 meters and went to their house there. And I think we could play that back now, right, and sort of see. And you can see that the velocity went up to like 30 meters per second. And I kind of was trying to find the exact spot there. And so the velocity and acceleration kind of went back and forth. So you can kind of record some bit of motion. It will keep track of the velocity and the acceleration, the net change in position. So that's one of the things that we can kind of do here. Let me try to reset all that. Let's kind of go back to normal there. Let's take a look at the vectors as we do kind of the same thing there. All right, so as you grab him, it's going to start recording. See, so the time is already ticking there. I'm not moving him yet. I'm going to move there, and you can see the velocity and the acceleration are kind of going in the same direction at first, but you see how the acceleration vector is kind of flip-flopping back and forth. And that's because when you first start moving the person, the acceleration and the velocity are going in the same direction. We have to accelerate the person to get them up to sort of non-zero velocity there as they move in that direction. But as soon as I began to sort of slow the rate at which I was dragging my mouse, across my mouse pad here, no longer is the person accelerating or speeding up in that direction, but I'm beginning to slow them down. Take a look at this. You can see right at the end of that, right? So I sort of dragged him all the way to negative 10 meters there. So I changed his position to negative 10. That indeed the velocity and the acceleration start out in the same direction. But once you begin to slow them down, that acceleration vector sort of opposes it. So you see that there. And that's because in order to slow something down, we have to apply a force in the opposite direction of motion. And we know from Newton's second law that force equals mass times acceleration. And so the direction of the net force, the direction that's going to cause that deceleration is, sort of in the same direction as acceleration. The force, the net force, and the acceleration are always going to act in the same direction. And if you wanted to, you could sort of play that back. So here he's sort of staying at 0 meters, moving, and you can kind of see that as you speed up and slow down, the acceleration vector changes. The velocity is always in the direction of motion, right? In order to sort of move that way, we've got to have the velocity vector in that direction. But the acceleration vector, is changing as we're slowing down, right? So as we're moving towards a destination, we begin to slow down and therefore decelerate. And that means that the acceleration vector will oppose the direction of motion. Let's reset everything here. Now, a good rule when you're exploring something with an inquiry lab or kind of looking at what the simulation has to offer here is to kind of, we say rats, read all the screens. So we've already kind of looked at, the velocity and acceleration vectors. We've got position, velocity, and acceleration sort of, we can toggle it this way, like so this is another way to sort of, move the man to where you'd like them to be with position. You can also do that for velocity. So if we set it to -4, you can see he's sort of in that direction. If I hit play, he's going to move at that velocity, right? Just sort of as long as you keep him there. Let's say if we change it to +10 meters per second, note that he's turned around because he knows, oh, +10, I'm moving this way. You can see that he's going to move faster in that direction. So indeed, you can set the controls to sort of how you want the man to move, and then sort of explore that motion. Note that we've been in the introduction tab this whole time. So if we look at charts now, here we can see that we've got the same quantities, position, velocity, and acceleration. We can also decide to show vectors here. And we're going to be generating a plot now of position, velocity, and acceleration as a function of time. And we can toggle the same sort of settings by moving the cursor here. So let's say I want to set this person, in motion with a velocity of, 6.281 meters per second. And you can see that they've already shown the velocity vector there. Once I hit play, they'll sort of move at constant velocity. So note that there is no acceleration if the person is just moving along at constant velocity. Let's take a minute to explore that. We see on the velocity time plot just a horizontal line corresponding to the velocity that I've set. We see that position as a function of time is just sort of this constant slope, right? And if we were to take the gradient of that, we would get this value here, right? So you can see like after 1 second here on the x-axis, see how it's moved just about 6 meters, right? Because the velocity is about 6 meters per second. Because I've set it to a constant velocity at the beginning of the motion, there's no acceleration. In other words, this in the simulation, we don't have to ever get up to that speed. As soon as you hit play, the object, the man, is just moving at that constant velocity, which is why the acceleration is 0. Let's reset that. And let's have the acceleration vector start at about, I think we can enter values here. How about 9.81 meters per second squared? And so this would be like a person, even though gravity doesn't act in the horizontal direction, let's suppose that there was a rocket pack on the back of this person that was going to accelerate them just as gravity would, and in a positive direction. So how long until this person hits this brick wall over here? Well, let's see. All right, and we can see that indeed we have a non-zero acceleration to begin with, and that means that we're going to speed up. So we start at a speed of 0 meters per second, and then as a function of time, we see that that velocity is a constant increase. If we were to take the slope of this velocity time plot, and we can zoom in on it and maybe be able to actually kind of do some of those calculations. If we were to take the slope of this part of the velocity time graph, we would be getting the acceleration because the gradient of a velocity time graph gives acceleration. Note that the position time graph is a curved line, and that's because the slope of a line, drawn tangent to this curve here is going to be the velocity. And so it starts out with a very shallow slope or a very low velocity, this part of the graph. And then as the speed picks up, we see that the lines drawn tangential to any point in the curve are getting steeper, right? Indicating a changing velocity or acceleration. So we see that this acceleration matches sort of the gradient here, matches the changing slopes of the lines drawn tangential to this position time curve. And we can explore all of those sort of ideas that are right at the heart of calculus just by kind of looking at this man moving there. And again, you could either just sort of pull the man and move him as you want to. A man who needs to go to the store and then go back to this tree and then slam into this brick wall over here. And then we'll pause that, and we could analyze sort of that motion and see what that looks like. Note that the position is changing sort of back and forth between, at 0, he's just right here where he started. So you can have negative position heading towards the tree, positive position heading towards the house, and the corresponding velocity and acceleration plots. There's plenty that you could do with this simulation, so this is just an introduction here. Note that you could always take a look at the special features like reversing the x-axis, and there's even an expression evaluator that will, it says enter an expression for position x as a function of time. They've got sort of this equation here that x is a function of time is 7 times the sine of time plus 2. So, just sort of play that, then you could see what's going on if you wanted to have an expression for the person's position as a function of time. And then looks like he's turned around here. He's heading back. And because of the sine function in this, you can imagine that the person may indeed change direction again, and their position as a function of time would just sort of be kind of like this sine wave. All right, so he gets through the edge here, turns around, and goes back. All right, I leave it to you to explore Moving Man to your heart's content, and be sure to be thinking about the sort of key physics ideas that will help you become a better student of physics, and that is the slope of a position time graph gives velocity, the slope of a velocity time graph gives acceleration, and the area underneath a velocity time graph gives displacement. So those are key ideas to think about. Also think about the direction of the vectors as a person, is moving. How the direction that a person moves in, right? So their position is increasing in the same direction as their velocity. As a person speeds up, the acceleration will be in that direction. You can kind of see that right now. But as the person begins to slow down, that acceleration vector will begin to oppose the direction of velocity, as we're seeing right now. And so here the person is slowing down. Have fun.